So now we can formulate the Heisenberg uncertainty principle we just discussed in terms of a formula. So it looks like this. It is the difference, the change of the momentum in the y directions multiplied by the change of the position in terms of the y directions. And the multiplication of these two has a minima value. The minima value is h divided by 2 pi, and h is a Planck constant. But let me explain again how to understand this one. So why it is a momentum in the y direction and the position in the y directions? It is based on the picture we have here. When we study the double slit, when you try to describe the position of the electron more precisely, what does it mean? Which means that all the electron will be centered at the central axis of the band here. So which means that the relative position in the y directions can be described more precisely, and it is relative to the central axis of the double slit. So therefore, if you try to determine the delta y more precisely, which means delta y is smaller, then you will lose the information of the momentum in the y directions. So this y direction is irrelevant to the information in the x direction or z direction. That is very important. So therefore, if you try to make the difference of the momentum bigger, you can get a smaller delta y. So the uncertainty will pass from the position to the momentum, and the smallest value is h divided by 2 pi. And we have learned that h is a Planck constant, very small. So therefore, Heisenberg uncertainty principle is only important when you are dealing with a particle at a scale of the 10 to negative 10, which is the scale of the proton or the atoms. So if you have a size 10 meter, 100 meter, it is way bigger than h, then there is no way you can see the quantum effect. So that's the reason the de Broglie and Heisenberg uncertainty principle are important when you study the small particles. So this is the first format of the Heisenberg uncertainty principle with relation about the momentum and position. But you will see this is second format is that the difference of the energy and the difference of time, and the multiplication is also have a minima value. So once again, it is the more precise the energy you want to describe a particles, then you will know that at which moment of the time it is. So this kind of the effect is definitely not be obviously at a microscopic scale due to the reason I just explained. So there's intrinsically uncertainty there. So this is related to another very important theory in the quantum physics is that we try to describe now an electron as a wave functions. So as a wave function, what does that tells you is that even it is a particles, but because they have a wave property and which is important at quantum scale, so which means ideally at this particular moment you have no idea where the electron it is. So this basically contradicts to our understanding in the classical physics. We always thought that at a particular moment and we always know the velocity, the position of a particle precisely, but not because of wave properties. And now the particles could be at a different corner in the room. Before you do the measurement, you have no idea where they are. And this kind of uncertainty is an intrinsic thing to understand quantum physics. So I understand a lot of things. It is probably not easy for you to accept. But we are not in the very advanced level of the class, so I'm not able to dig into more details. So the final topic of the chapter 30 is the tunneling. So people originally they thought, wow, this is a crazy concept. So what the quantum tunneling is saying is that if you build for example, a mountain here, so you can treat the mountain here as a potential gap, okay? So we can use the concept of the electric field. So if you produce a voltage difference here, a potential difference, or the gravitational potential in that case. So if you have a particle moving, So ideally, if you are not provide enough energy, there's no way you can overcome the potential energy, the potential gap, and the passing throughs. But it is true only when you think it is in terms of the particles. Because now, based on the de Broglie duality concept, the particle also have the wave properties. So even you have the gap or the potential wave there, it seems impossible for a particle to penetrate through. But if it is a wave, then they might have some possibility. You will say that how could it be even it is a wave? So that's the reason we studied the chapter 14. So we know that when the wave propagate in the, for example, in the fiber, they will have the total internal reflection, yeah? So the light always will be constrained within that. But if it is not the optical fiber, it is something different, a mirrors. And what you do is that you try to produce a small gap between the mirrors. So originally it is one, but you produce a small gap. So the wave will propagate in the mirror. So most of them will still going through the total internal reflections. But you know that some of them might have a chance to be reflected. And they will enter into the gap and then enter into the second mirrors. So the particles coming from this mirror, this side of mirror to the another side of mirror is the concept of tunneling. You can consider this is a potential well, a gap. But apparently if you make the gap wider and wider, so this part of the mirror is further away, then you will find out there's no way you can see that a wave is propagate and penetrate through this potential well and gap and enter into the second part of the mirror. So which means the bigger the potential well or the deeper the gap it is, the chance for the particles as a wave will be transmitted will decrease exponentially. So the further away these two mirrors it is, the less the chance for the particle or the light can penetrate through and passing through the gap and enter into the second part of the mirror. This is a quantum tunneling in terms of the light as a wave. But now you can think in terms of the particles and a potential well. So in the lab in this coming tomorrow on the Tuesday, I'm going to give you a short version of the simulation of a particle behavior in the box. So the concept of box there is a potential well. So you can consider that is if you try to put the particle inside that box, how high the chance, the probability the particle will penetrate through the well and leave the box. And that is the quantum effect of that. And one of the most important application for the quantum tunneling is for the microscope. So ideally, how do we try to probe the structure of atomic surface? Actually, we cannot see that. So the way we can probe the surface of the atomic surface is due to the surface of the atomic, they have different kind of potential well, or you can use the gap, the concept of gap to understand that. It is not a smooth concept. So when the tips of the microscope passing through the surface, they will sense the tunneling effect of the electrons differently. And due to this effect, they can determine the relative structure on the surface of each atoms or the molecules. So intrinsically, when you try to probe the structure at this scale, you have to use the quantum tunneling. So we just finished our discussion of the chapter 30, and today I'm going to start our discussion of the chapter 31. But once again, I'm not going to cover everything in the chapter 31, so please treat that the chapter 31, these 4 sections are just the continuation of the chapter 30, because you can see now here I'm going to introduce you the concept of atoms, the spectrums, and how do you relate the so-called de Broglie wave to the model of the atoms. So let's try to go back to the history. So the idea that the matter is composed of a discrete unit, and this discrete unit is the most fundamental one. They cannot divide it into the arbitrary tiny object, can be traced back to millennia ago. So this is a clay find out in the 18th centuries at the Iraq. And there they have 1,000 lines which is recorded during the old Babylonian time. That's actually the particles the matter is made of the discrete unit. So the first theory, actually, people accept can be traced back to this period of time. They propose that all the matter is composed of air, earth, and water and fire. So I have to say this is a very crude way to understand that, but it seems that no matter in the Eastern culture and the Western culture, people all have this kind of guess. So this is the first theory, but theory doesn't mean it is true. You need the experiment to prove that. So actually, the theory, the models proposed by the Democritus is the first more close to the real model of the atoms. He said that this kind of matter is made of individual tiny things. Instead of this air and fire and water, they are made of tiny things and they cannot be seen from your eye. So no one actually paid attention to these theories until 2,000 years later. So the first time in the human history people can verify this argument is more close to the real concept is at early 19th century, that there is a chemist, the John Dalton's. He performed that actually there are a lot of the small structure, so-called atoms. So which means now we are at the beginning era that we can break the matter to the scale of the atoms. So to this class, this is enough because we know that in order to connect it to the chemistry, the periodical table is made of different kind of elements, and for each element, it is made of a single atoms. So we know that there are 118 atoms there, and we know that different kind of atoms can combine together to form the molecules. So we go to the area of the biology. So knowing how to describe the structure of atoms is already enough and useful for our discussions. So the lecture on the Wednesday, I'm going to show you that how people start to build the most realistic model of the atoms.